Great pleasure to have Sumilan Bannerjee here, and he's going to start his lectures on the SYK model, quantum chaos, and dynamical transition.
Yes, thanks, Onkar. Okay, so first let me thank the organizers for inviting me to give this set of lectures. So I'll be talking about Sachdev-Ye-Kitaev model, but from the perspective of condensed matter physics mostly. So I hope some of you, most of you probably working on string theory, high energy and quantum gravity finds it useful because of course Sachdev-Ye-Kitaev model has been studied by this community a lot. So I'll try to give sort of a part overview of SYK model and related developments in these 3 lectures. I'll also try to work out a few things on the board, some very basic stuffs about SYK model. So hopefully that will be useful for at least the beginning students. Okay, so that's the plan. So this lecture I'll mostly try to introduce the SYK model and its large and saddle points and different relations to some questions in condensed matter physics. And then next lecture I'll also talk about experimental realization of SYK model. I mean, some of them are just proposals, but some of them there are some experiments that have been done in condensed matter system. And I'll also talk about some related models which might be also interesting. And in the 3rd lecture, I'll talk about some non-equilibrium dynamics and entanglement calculation in large N SYK model. Okay, so let me start. So first of all, again, just for the people who are not familiar with this topic, so there are of course many references. Certainly, I mean, it's worth listening to this talk by this set of talks by Kitaev at YITP lectures. So I'll certainly recommend that. And then there are many works, sort of long papers written on this. So this is one of the early and very detailed work which looked into this, Maldacena and Stanford. And then there are some recent review articles, relatively recent review articles, which is in Review of Modern Physics, which looks into more perspective of condensed matter and non-Fermi liquid. And then, of course, there are papers by Kitaev also, which are also worth trying to read. So there are many other references. I'll give some other references in case you are interested as I go on. Okay, so let me at least start with the motivations at why these kind of models are interesting to condensed matter physicists. And as I'll discuss maybe in the second talk, so the SYK model originated originally from a model of spin glasses, which is known as Sachdev-Ye model. And I'll discuss that model a little bit. And even when this Sachdev-Ye model was studied in 1990s, early 1990s, the interest was to understand this kind of things called strange metal or non-Fermi liquid behavior. Okay, so let me just give some experimental phenomenology of this strange metal. So what I am showing here is a phase diagram of copper oxide superconductors. These are these high TC cuprates, kind of famous material. And what is plotted here is temperature and some chemical doping, chemical tuning parameter, which is some doping, the number of, essentially trying to control the number of carriers in the system. Now in this phase diagram, there are many phases, and of course, I mean, this phase diagram has not been completely found. I mean, even experimentally, I mean, there is probably not a single phase diagram. If you take many different compounds, so similar behavior. So of course, it has this famous high TC superconductivity, which has pretty high temperature, 100 Kelvin. I mean, it can go up to higher temperature under pressures and other thing. So apart from various different phases, one of the phases that was sort of interested people a lot is what is over here. So between these dashed lines. So here, so this is the phase which is known as strange metal. So now what is strange about this phase? So when people did these measurements long ago, already it was quite strange, and then as the experimental progresses, it becomes stranger and stranger. I'll not discuss that all the phenomenology that much, but so essentially, so the first evidence of the strangeness of this phase came from these resistivity measurements. Okay. So when you measure resistivity, so generally the resistivity is coming because electrons are getting scattered from various things in the system, for example, impurities, phonons and electrons themselves. So then there are various contributions. If you look at the book by Ashcroft and Mermin, so there will be these different contributions to resistivity. So what you are trying to do, you extract out the electron-electron contribution to the resistivity. Okay. So that's why it's written del rho t. So if you look at the electron contribution of resistivity, so the standard theory that we know how to deal with, which is this Fermi liquid theory. So that will give you a electron-electron resistivity, which is goes like T square. Okay, so this is typically what you will see at low temperature. Of course there will be a contribution because of impurity, because there will be a constant contribution, but then the resistivity will increase as a function of T squared. Then eventually it will be dominated by phonons at higher temperature. So now, but here what people found that after even all these subtractions and all the things that you can think of, you find that the resistivity was linear in T. Of course, this linearity resistivity is not very surprising at high temperature. Even electron phonon scattering above the Debye temperature will give you linear in T. But the thing is that this continues up to very low temperature, and people have gone to lower temperature by applying magnetic field and destroying this superconductivity. As low as you can go, it continues to be linear in T. Okay, and without any change of slopes or anything. So meaning that there could be linear in T resistivity because of electron phonon, or let's say for some unknown electron mechanism. But generally then you would expect that this mechanism, different mechanism will kick in at different temperature, and maybe the slope will change. Nothing like that is seen. Okay, so that's one indication of non-Fermi liquid, and this is quite generic. There are other material, for example, these iron superconductors, which are quite different from this ITC material if you look detail of the phase diagram. But what is plotted here is essentially experimentally extracted, people have extracted this exponent gamma and then plotted it. As you can see that in this region, this gamma is showing red, which means it is 1, close to 1. Okay. And you can see this indication even in spectroscopy, which you can actually do, measure this, essentially you measure the electronic Green's function by this spectroscopic technique or the self energy. So, so what you find from these spectroscopic results that typically the self energy will go like at low, so this is a metallic state. So at low frequencies, this should go like omega to the power alpha, as omega going to 0. So now again for Fermi liquid, that this alpha should be equal to 2. I mean in general it could be greater than 1, which essentially means, so this is kind of the definition of Fermi liquid you can take here, which is that if you look into this expression, then as you are going to lower and lower energy, then at very low energies ultimately this term become irrelevant. Okay, because it has a power omega to the power alpha, and alpha is greater than 1. So always this term, omega term, will dominate. So essentially it is becoming non-interactive in this fixed point. So that's the Fermi liquid fixed point. Okay, however, for this region here, what you find that this alpha is less than 1. So essentially it means that, of course, experimentally you cannot go to arbitrary low energies. But it means that up to the lowest energy you can go, it looks like that the interaction effect is dominating. Okay, so this is another characteristic of non-Fermi liquid. Of course, this kind of characteristic has some issue, meaning that here it actually kind of a basis dependent, because when you are defining this Green's function, so it's a Green's functions. Essentially, I have not written here, but this what you measure in this angle resolved photoemission experiment is essentially the spectral function of an electron with a momentum k. So this momentum k is of course a single particle basis. So this thing is somewhat basis dependent, because of course you can choose a wrong basis and you can get a self energy which is much larger. For example, if you take a tight binding model, but if you which is a model where the momentum is what diagonalizes the model, the non-interacting model. But let's say if you choose the basis of site, okay, so then of course in that basis the self energy will become very large, right? I mean, if you define it that way, because you are choosing a wrong basis. So there is such issues, especially if you have disorder in the system, so of choosing the right basis. So this is cannot be a completely universal definition of non-Fermi liquid. So you have to rely on multiple things. For example, the resistivity, and then there are other things. So these other things is where sort of this Sachdev-Ye-Kitaev model also comes in. So you can then ask that can there be more sort of broader or other at least complementary probes of to distinguish non-Fermi liquids and Fermi liquids. And it turns out that at least for this kind of non-Fermi liquids, this Sachdev-Ye-Kitaev model, it turns out that the answer is yes. I mean, you seem to be able to distinguish yes. Yes. Right. No, I can, yeah, okay. No, so what I was trying to tell is that, so typically when you are trying to obtain the Green's function, so I didn't write it there. So these Green's functions, so you are writing it in some, so when you are doing in the RPS experiment, this experiment that I was mentioning, so essentially you are trying to find out the spectral function of a electron at a momentum k, okay. So here you have chosen a single particle basis, and in that basis, because originally for the non-interacting system, this is a good, and translational invariant system, this is a good basis, right? So then if you don't have any interaction effect, then this will be sharply well-defined quasi-particles, right? So of course, so now this self-energy is making them ill-defined quasi-particle, but let's say I would have chosen a different basis, I would have written this problem in the real space. Right, so then of course this Green's function, so essentially I am thinking about a tight binding model here, okay, so some model like this, right. So if I write in this basis, so this basis, this Green's function or the spectral function will look extremely broad, right, because I have not chosen a right basis. Yeah. Yeah. Yeah, right. So you have to, right. So in the RPS experiment is somewhat similar. So you are essentially catching the electrons after sort of, it's like a scattering experiment, right? So you are trying to do that, but still what you are trying to guess is that, so you are trying to reconstruct the electronic state inside the material. So yeah, maybe that, you can do it, but yeah, I'm not familiar with that thing. But yeah, I mean, that would be an idea, I guess, if you, from the scattering experiment, try to, yeah, but when you mean the pole, you mean in the single particle spectral function? Okay. Yeah, so, right, so you can, of course, okay, maybe I can talk to you about this. I'm not familiar with this. Yeah, because the way, so here also you are trying to find the pole, but since you are sort of doing this experiment assuming a translational invariant system, right? So you will not, even if there is a pole, if you choose a wrong basis, you will not be able to easily see it. Maybe there is a way to reconstruct that. Yes. Yeah, can I have the slides back, please? Yeah, just a minute. Yeah, sorry, which graph you mean? Yes. Yeah, so this, okay, so there is some, so I don't know what is called S shape here. So generally, so this is a different regime, okay, so this regime I'm not in, so this is called the pseudo gap regime, okay. So here what happens is that as you, so initially there is some different temperature dependence here. So typically it is like T to the power some high power. So basically if I plot the resistivity, so in that region, so it's sort of course there is some, there is superconductivity somewhere. So initially sort of it goes and then eventually become linear. Okay, so that's what probably they are calling S-shaped. I don't even remember what. So, but this regime is not relevant for this discussion. Okay, so the question, so the thing is that so you want to define it using this many body quantum chaos and thermalization. So I'll discuss about this trying to use thermalization to detect non-Fermi liquid versus Fermi liquid in the last lecture. Okay, let me introduce a little bit this many body chaos. So this is characterizing using this kind of thing which is called out of time ordered commutator. So I'll discuss this in bit more detail later. So essentially you calculate this kind of commutator square. So you take two operators, one at a time t and another at some other time, let's say t equal to 0. And then if you have a many body quantum chaotic system, then what is expected is that this quantity will grow in this form, e to the power lambda L t. However, I must say that this kind of thing is not very generic, in the sense that typical quantum many body system that one studies in condensed matter, for example, Hubbard model. So there you will not find such region where actually this quantity grows like e to the power lambda L t. Okay. Yeah, so that regime of time, typical strongly correlated material is very small. Okay, so it's because of this. So this region of time is essentially determined by some semi-classical parameter, which in the semi-classical chaos is h bar. Okay, so 1 over h bar, sort of log of 1 over h bar gives you the time window, and in large n theories it is given by n. Okay. Yeah, so after that typically it will saturate because of the quantum interference effect. I will talk about this a little bit in the next lecture. Okay, but generally what happens is that this window could be very small. I will come to this point more detail. Okay, and you may not detect it. So this kind of diagnostic, although nice, but it only work this kind of large n type models. Okay, or some weakly interacting model. Yes. Yes. No, there is no, there is no expectation. So it was used because in the SYK model, there is some kind of a semi-classical parameter, okay, which is this large n parameter. So that's why it is useful in the SYK model. So in general condensed matter models, it's not useful typically. Yeah, so Hubbard model, you can't detect this region where you have this exponential growth. It's not valid because you can't, simply is not a practical probe. Okay, that's why it's not valid. I mean, valid meaning, of course, there could be a region, very small region, it grows, right? But it's ill-defined, some order 1 region. I mean, you can't define exponential growth with very small region, right? Okay, so now other thing is this kind of thermalization in isolated quantum systems. So essentially what you are trying to look at is the thermalization rate. And so this I'll talk in the last talk. So essentially question is, so the extreme limit, the question is you start with some initial pure state, okay. So and then the state evolves, but in some sense you are still able to define a kind of an ensemble, which is essentially you look into some expectation value of some operator, maybe average over some time window of experiments. And this expectation value, which just came from evolution of a pure state which remained pure, may become equal effectively to some average that you can construct using, let's say, the energy of the initial state. Okay, so which is some thermal average, and so this correspondence may work. If this works, then you say that basically this is thermalizing, and you can ask that how fast it is thermalizing. okay, and whether the Fermi liquids and non-Fermi liquid are distinct in this context, in this regard. Okay, so this is of course related to the eigenstate thermalization hypothesis, that typical many-body system will thermalize in this sense. So still the question is how fast they do it, and that can distinguish these different phases. So I will give one example using Lyapunov exponent. Okay, so let me just very basic thing about chaos, as he was saying, that is just a semi-classical or classical concept. So originated from this single particle chaos, which is essentially you have a chaotic system like this, and you start the initially two trajectories which are very close by. So which is very close by, this delta x0 is very small. And then because of the chaotic dynamics, if you look into the difference between these two trajectories, which initially was very small, it grows exponentially over some window. And this window you can make very large by choosing this delta x0 very small. Okay, so you can make this window very large. So it can continue for arbitrarily long time. So there is this handle you have in classical physics, by choosing this initial condition, you can make it very the time very large. Okay, and you can see this. So now the idea that of this OTOC sort of originally came from this work by Larkin and Ovchinnikov, who used it in some context in studying superconductors. So basically the idea is that you take this object and then you write it to like a Poisson bracket. So you can write this object as a classical Poisson bracket, and then try to do a quantum semi-classical correspondence. What you do is you replace the Poisson bracket with a commutator. Of course, you have to put some dimension here, which is the h bar. Okay. Yes.
Since we are looking at at times very larger, so can we not say that this delta x0 need not be very small to start off with, but can be arbitrary?
No, so the thing is that so this regime of growth is a linear stability regime. Okay, so essentially what you are doing a linear stability. So of course the non-linear effects will come in. So if you make the initial delta x large, so then this non-linear effect will come in before. Okay, so once the non-linear effects come in, then you will go away from this linear growth regime. Okay. So then you have to really take into account the complete fully non-linear effect. So this linear Lyapunov exponent is defined using some linear stability analysis. Okay. So that's why you want to make the initial window very small, so that you can study this linear stability regime for a long time. Okay. Okay, so that's so now what you do is, of course, you in quantum mechanically you have to define some state and you have to take a expectation value. But if you just take expectation value of this, then it will just give you standard 2-point functions. Okay, and we know that standard 2-point functions do not really grow; they generally decay, right? So of course that will not work. So it turns out that if you square this object and then take expectation. Now this expectation could be with expectation with some pure state, or it could be expectation with some thermal state. Okay, so in that case you will have a temperature which is designating the state, and then you ask whether it grows like this. So you can now, of course, this was for a single particle system, but you can generalize now and hope that it works even for many body system. So you just take two operators, maybe two operators which were initially commuting. So initially this quantity was 0, but then you at later time this grows, and you get some exponential growth. And the reason it grows, of course, is because if you write this operator, initially this operator was has some local support which has no commutator with some another local operator B0, but as the time evolution goes, this operator of course will no longer remain that initial operator. It will become a different operator altogether, and these different parts will be generated by this nested commutator. So it will become more and more non-local, and specifically for interacting system, this operator will grow. Okay, so in non-interacting system, it will not grow very large because this nested commutator will kind of truncate, because if you have a quadratic system, but interacting system typically it would grow. Okay, very fast. So now you can take this thing and also define a part of this. So essentially you expand this object. So then a part of this will be like a standard time ordered correlation function. But then a part of it which will look very different, which will look this out of time ordered object. Okay, so if you just expand this commutator square, you will get a piece of this. And the idea is that if this one grows, then that piece, okay, so this out of time order correlator will decay, but decay in this very particular form, which is different from exponential decay. Okay, is something minus e to the power some time. Yes. I mean, it can still grow in some power law fashion, okay, but generally, I mean, it will not grow exponentially. Yeah. No, I mean, you can of course take certain case where it will terminate, right? But of course, you can take a situation where it doesn't terminate, but it will still remain it will not grow very fast because everything will still remain quadratic, right? So, I mean, of course, depends on which operator you are taking. I mean, if you already take a kind of a non-local operator, then, but it will ultimately sort of terminate because this Hamiltonian is just a quadratic operator, right? Yeah, it's related to the conserved quantity, right? Because in the non-interacting system, if you diagonalize, then there is a single particle basis, and for that basis there is this conserved quantity. So it's related to that conserved quantity that it is not there. Yes. Yeah. Okay. So now, so just to get into this SYK model, and let's start with a non-interacting sort of warm up of a non-interacting model. Okay. So which is just a non-interacting random matrix model. So let me define the model. So it's also called SYK2, but this model has been used for many long years. So here is the model. So essentially you have n sites, I1 to n, and then essentially it's just a tight binding model, but all-to-all hopping. So all the sites are connected by hopping to any other site, right? So essentially I have tried to draw. So there is complete connectivity. Okay, so all sites are connected to every other site, and then this object that appears here is this hopping, which is actually a random number. In this case, I have taken a complex random number, which is drawn from a Gaussian distribution. Okay, and so turns out to define the thermodynamics like extensive energies and all, you have to normalize the prefactor by 1 over square root of n. Okay, so that you get extensive energies and all. And since I have taken a complex fermion, then I can of course change the number of fermions, and so that gives another tuning parameter, which is the chemical potential. Okay, so this is the model. So this is just a n cross n non-interacting random matrix model. So yes.
What is this? CI dagger CI. Is this like hopping on itself?
It's just a on-site potential. Okay, so it's like just a potential, it's like a chemical potential, it's just mu n, right? So that sum over I, Ci dagger Ci is just total n.
No, it's in terms of tight binding, so it's like within the unit cell.
Yeah, it's just like you have some kind of energy cost of occupying that site, right? So if you occupy, it feels a potential mu. So if you have Ni equal to 0, then it doesn't feel anything. If Ni equal to 1, then it feels some potential. Okay, so this is how you try to tune, like essentially I'm trying to write the grand canonical ensemble in a different way. Okay, so now, so the origin, so you can of course write a Majorana version of this thing. I mean, not exact transformation, but Majorana version which has exactly the same physics, but at mu equal to 0. Okay, so if you take this model and if you take mu equal to 0, which is called the particle hole symmetric case, so this model, the physics of this model will be exactly same in this large n limit with this model that I have written, okay, which is a Majorana version. These are Majorana operators. Okay, so now this model, of course, either of this model, because it's just a non-interacting quadratic model, you can diagonalize. So for example, at least numerically for finite system, you can diagonalize up to very large systems. right? So just diagonalize this matrix Tij. Now remember that this Tij is drawn from a disorder, a random Gaussian distribution. So what you have to define here is different realizations of these Tijs, right? So it's like a disorder system. So now, of course, if you do experiment on a particular disorder system, then this is our realization of the disorder. If you do it in another lab, then there will be another realization of the disorder. Now, the idea is that the quantities that we are going to be interested in mostly what are called self-averaging, which essentially means that in these different labs, whatever you measure, that particular quantity will give you same result. Okay, although these realizations are very different. Now, the way you try to understand this is by when you do theory, you try to average over this disorder. Okay, and of course, but you have to remember that the experiment is done on a given realization; it's not averaged over disorder. But if the quantities that I am interested in are self-averaging, then you will get the same result, okay, or expected to get the same result. But all quantities are not self-averaging, so you cannot take a wrong quantity and try to ask whether these two measurements agree. Okay. So now, if you take a given realization, okay, which I am denoting like this, then given for that given realization, you can diagonalize the system. I am taking this one, and it will give you some eigenvalues and single particle eigenfunctions. So, for example, if I had instead of this, if I had a standard tight binding model, which I was writing here in answering Suvrat's question, so then this alpha will be basically the k, right? But in this case, this alpha will be some complicated object because this doesn't really have any pattern for some random distribution. So now, given this, you can, I mean, in this model, given these eigenfunctions and eigenvalues, you can basically calculate anything in this problem because it's a non-interacting problem. So the particular thing that we'll be interested in is this single particle Green's function. Okay. So this single particle Green's function I have defined this way. So this is defined using the Heisenberg operators corresponding to this, but this evolution has been written in imaginary time, the Euclidean time. And then this is the definition. So I have defined it this way for some thermal state, which is defined by this expectation, right? So I just look into this quantity, I take an expectation. So right now I have not averaged over disorder. So this will depend on Gij, and then I can do different kinds of thing with this. I can look into this in what are known as the Matsubara frequency. And then I can do some analytical continuation from the Matsubara frequency to obtain what are known as the retarded Green's function. Okay, but this system is in thermal ensemble, so only one Green's function is enough. You can calculate any other Green's function if you know one of them. Okay, so this is the quantity you will be interested to calculate. So now let's try to do this calculation. Okay, so now the first thing is we are interested in this large n limit n going to infinity. So so the idea is, and I will try to show it very quickly on the board. So if you look into this this quantity, then so if you look at in this large n limit, then this Gii, okay, so this Gii tau, so that will actually not depend on I. Okay, even for a given realization. And then this is same as if you average over different type, because it is same. Okay, and it will turn out that it is same as if just taking Gii and doing a disorder average. So this is a self-averaging quantity. Okay, and the averaging I am doing is this. Okay, so here I will go to the blackboard and try to sort of very quickly do this. Any question before that? Yes. Yes. Yeah. Yeah. Okay, so to sort of so the standard large n calculation that you do here. So so there, of course, I'm going to just do a disorder averaging, and that I'm just doing the disorder averaging. So this result will come out, but that doesn't explain why this disorder averaging is valid. Okay, so for that I will use some another method which is called the cavity method. and I'll just explain that cavity method quickly. Okay. Okay, so here what you are trying to do, as I have written there, so I am trying to, so what I try to do here, that I have this, so I have this model. So what I do here is that I treat this Tij as a perturbation. Okay, so essentially it means that so the initial starting point, so the H0 that I am taking, so maybe it's too small, I am writing, but it can be seen here. So this initial H0 is just an on-site term, okay, which is just Ci dagger Ci. Right, so given that, you can just calculate the Green's function for this problem. It's just a single decoupled, I mean essentially decoupled sites. It's just a single site problem, right? So, so as a result, the bare Green's function for this problem, again you can write it in the imaginary. So by the way, this omega n I'll be using is the fermionic Masuvara frequency. Okay, so this is the bare Green's function. So now what you have to do, so you have to put, yes. Yes. T is the temperature. Okay, so remember I am doing a thermal theory. Okay, so I am trying to calculate the Green's function which I wrote. So I am trying to calculate this Green's function, which is okay. So the T comes from this averaging. Okay, so the T is just 1 over beta. Okay, so given that this Green's function has a KMS boundary condition. Okay, so that will tell you that if you write it in the frequency space, so then okay, and this so since this object, so you can write the inverse Fourier transform. Since this object has to be antiperiodic, so this I omega n has to be of this form. Okay. Okay. So now, so basically you are trying to treat the perturbation of this hopping term. Right, so this is my vertex. So then, so you are trying to look this look at this full Green's function. And remember, the bare Green's function only has the on-site Green's function. It cannot take you from one site to another distinct site. Okay, so this is the bare Green's function, which is on-site. And then, so now what I'm going to do, I'll first do this disorder averaging, right? So, and remember, if you are doing disorder averaging, then so only thing that will be non-zero. So if I take Tij and Tk alpha, and then I'm trying to do disorder averaging, so this will become T square delta Ik and or other way around, del I L Kj. Okay, because originally I have a Gaussian distribution where this different pair of the hopping between different pair of sites are uncorrelated. Okay, so this will be just, so essentially this is the only non-zero term. So now if given that I have very strong constraint here, so as you can see that I can try to, of course I cannot take this diagram and just, yes.
So in them, what are the diagrams?
Yeah, so I'm just drawing the diagram in the real space. Okay, so essentially I have a bare Green's function which is like this because I have only term in the Hamiltonian which is on side, so it doesn't propagate from any side to any other side. And then I'm trying to treat this hopping as a perturbation. Okay, so this one I have just writing as Ci dagger and this is Cj. Okay, and then I have to contract. So I start. So I'm trying to calculate this object. So I have to contract with some external legs here. I am now going to look at the average. So this bar means that this average is not thermal average. This means averaging over disorder. I'll show that. Let me just show this quickly, then I'll show the other. So this method you cannot show self-averaging. This is assuming self-averaging. Okay, so this is not right. Yeah, so sorry. Yeah, I'm right now just doing the large n way of doing, which is just disorder average Green's function. Okay. So here you are assuming self-averaging. You are not proving self-averaging here. Okay, so now you see that I cannot average, so I have to average this. So first diagram I will average with this diagram. So I contract this and then I get this and then I have to average this. But if I average this dashed line which is showing TIs, it will just give you 0 because this distribution has 0 mean, right? So then the only sort of non-zero diagram that I can think of is this diagram. So I'll just write it like this, right? So here by this what I mean that I have to also contract the disorder line. Yes. Yes. So it's a complex number, okay, and it's uncorrelated between pair of sides. So this so the distribution. So of course the total distribution is a product. So it will have to do I less than this. So dTij is 1 over pi t. So remember that there is a hermiticity constraint here in this Hamiltonian that I have written. The Tij has to be equal to T star Ji. Okay. Okay, so this is sort of the only diagram that will contribute in this order because you have to contract also the disorder line. Okay, I am now doing disorder averaging. I am not showing self averaging. I am just doing disorder averaging. Okay, and so now you can think of drawing the next diagram. So the next diagram, of course, having this 4 vertices. Okay, because you have to have at least even number of vertices, right? Because you have to contract the vertices also. So 4 vertices, but now you can draw it different ways. You can have this non-crossing diagrams, and you can have crossing diagrams, right? So again the constant is similar. So this whatever you put it here, this has to be the complex conjugate. So if you draw this and if you do the disorder average, you will see that this diagram actually you can't even draw. I mean, meaning there will be some trivial diagram where all the sides, I mean, you can try to see this. So essentially, remember when you are trying to do this, so wherever you come out, so there also you have to have the same indices, right? So you have to have same indices here, and similarly here. Because so whatever, so like if something I goes in and j go out, that is Tij, and the other diagram should be I go out and j goes in. So then only you can contract that, right? And as a result, if you are trying to draw these crossing diagrams assuming disorder averaging, you will see that these are under disorder averaging, these are just 0. Okay, so this diagram is however non-zero. So here you can see that you can do this. Okay, and you can estimate what is the order of this diagram, right, without really writing the full thing. So the order of the diagram, as you can see, that I basically have a Tij. So I is fixed because my external line is I, right? So Tij mod square. So I have a summation over j because j is the internal index, and then I have here another Tjk. Okay, so I have two summations. And remember that these factors came with a 1 over square root of n. When I defined the model, there was a 1 over square root of n. So this will have 1 over n here. Yeah, so yeah, sorry, this, so I'll have essentially 1 over n square here, and I'll have these two summations, right? Because 1 over n square, because I had 4 vertices. Each vertex gives 1 over square root of n. And then there is this two summations only, okay? So of course, if I disorder average, then this just giving me t to the power 4, and then I have two summations, which gives me n square. So that you can see, of course, there will be some Green's function here, but this is order 1. Okay, so essentially this series will continue, this non-crossing series, and basically you can write the full Green's function as like this. This is my self energy. Okay, and this self energy is nothing but T square G II tau. Yeah, because okay, this model is no longer yeah. So this the model. So let me write the model. So this is the model that I was defining. 1 over square root of n ij. Okay, so wherever I am putting this these dashed lines, so that's my hopping line. So each hopping line comes with 1 over square root of it, right? Because I am just doing, so I said I am doing perturbation in Tij. Actually, I am doing perturbation in Tij by square root of it. Okay, so this essentially will give you a Swinger. So exact.
I have a question.
Yes, please.
I'm a bit confused. I'm a bit confused about the third term. So in the third term, you assign the index I, and I'm not sure index, but like
yeah. So this I didn't draw. So if you try to draw it, you will see all indices has to be I.
all indices have to be I. Why is that? I thought like
yeah, because let's say you can. I mean, okay, you can try this. I mean, I don't want to. So you can. So let's say I put it J, right? But then I am contracted here. So that essentially means that this has to be also J. Right?
Yes.
But then this is J, and this is I. So that means I has to be equal to J.
I see. I see.
Okay. So you can try it. I mean, basically, yes.
And also, what is that? What do you mean by double lines?
This line
Yeah.
is like full Green's function.
Full Gaussian.
Yeah.
Okay, thank you.
Yeah. Yeah, those diagrams I am not drawing. Of course, they are there, but in the self-energy approximation, so those are sort of the disconnected diagrams. So I am not drawing the yeah, of course, there are all disconnected diagrams. No, I am just trying to sort of estimate the self-energy. I didn't draw the disconnected diagrams. Okay, of course, there is a, for the corresponding to this, I have, of course, this diagram. Right? But when I write the self-energy, that will go away, right, in the Dyson series. Yeah, so for this this OA, so what you will essentially get is a equation, the Dyson equation. Let me go back to the. So you'll get a Dyson equation which is given like this. So this is so this G I omega n, as I said, is the disorder average Green's function. Okay, so this of course doesn't answer Suvrat's question, which is that I'm not really showing self-averaging. I'm just doing a disorder averaging. But how do you know that this is actually going to hold, even if I don't assume disorder average? So this model you can actually show this. But for this you have to use a different method which doesn't use disorder average. Okay, so let me just describe this method. So this is called a cavity method. Okay, so I'll not, of course, I mean, if you have to, it's a trivial algebra, meaning some Gaussian integrations, but if I have to write it, it will take time, but I'll just write sort of the main steps. Right, so in this method, what you do is you just write a path integral for this Euclidean path integral for this problem. Okay, so I am writing in the Euclidean path integral, and you can and of course you are using this coherent state, the fermionic coherent state, which are the Grassmann variables. Okay, to write this. So, you of course, so this is just a non-interacting theory. So this will have essentially you can write it as in terms of the bare, I mean the Green's function. Okay, so this is not disorder average. I am just writing the. So you can write it. Okay, so you can just write a Euclidean path integral like this for this problem. So then, so now this is a completely Gaussian theory. So I can just decide on my own, like I mean, I can just decide to integrate out some fermions and keep some other fermions, right? I mean, I can just do it this integration, the functional integrations, whichever way I like. So here, what you do, you choose, let's say, a particular site. So let's say I choose I equal to 0. And I integrate out all other sides, right? So basically, what will happen is that if I expand this object here, so essentially what I am doing is I'm just not writing all the integrals and all. So those are there, but so I have a term for the where I equal to 0, j equal to 0, right? So there is a term like that. And then I'll have a term which is I going to some other site, right? So let's, 0 going to some other site. So that will be like C0, G0 inverse, 0, I, C0, and then kind of the conjugate of that. Okay. And then I'll have a finally terms, so this I is not equal to 0. And then I'll have a term which is Ij not equal to 0. Right? And what I do is I just do a Gaussian integral. I just integrate out this thing. Okay. So this is the step I'll skip. I mean, this is, you can just try, it's very simple. Just a fermionic Gaussian integral. So this is what you will find. Okay. So let me write the sort of the final result. And here I have not assumed any disorder average. Right. So I am doing it for a given realization of disorder. Yes. Hmm. Mm-hmm. Hmm. Yes. Mm-hmm. Yes. Yes, yes, exactly. Yeah, that's all. Okay. Yeah. Oh, that's what you're. Yeah. No, that's right. But so yeah, but the thing is, no, that is true. I mean, you because these are just sum over the sides. Right. You can do. Yeah, that's true. Yeah. Okay. Yeah. Sure. Yes. Yeah, so that's exactly true. So if you write the, so let me just complete one more line of this. Anyway, so you can work it out, but the main point is that you get, so you get this term, which is the bare Green's function, which is basically this, okay, at the S side, and then you get this extra bit, okay. So now exactly as, I mean, it's the same result essentially, as Suvrat was saying. So if you just write it out, this term, given whatever I have defined for the Z0 inverse there, right? So I have defined the Z0 inverse. So you use this. So remember that the Green's function that appears here is what is called a cavity Green's function. So it's a Green's function where this zero side has been removed from the lattice. Okay, so this is that Green's function. Now, yeah, maybe I should write it here. Yeah, so this term, this second term, okay, so you can write like this. So now, so remember that this Green's function that appears here, I don't yet know it because this is the Green's function with one side removed. This is not my original Green's function. Okay, so because basically I had this all this connectivity like this, and then what I have done, I have removed one side. So this is Green's function of rest of the side. So this is, I don't yet know this. Okay, this is sort of an unknown quantity as yet. But what I know is that this Green's function doesn't depend on T0i or T0i, T0 nothing. So it doesn't depend because this hopping actually couples this side to the other sides, and since I have removed these sides, this problem, this Z0 doesn't have in when I am trying to find this Z subscript 00, then it doesn't depend on this hopping. Okay, this T0i and T0i, Tj0, right? Because I have removed this side. Yes. Huh. 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 Right. Yes. Yeah, yeah. This is just, no, of course, but the thing is that you will use it in a thermodynamic sense, right? So it doesn't change the wave functions or basis or anything, right? It's just a concept shift. So this number I use to tune my number of fermions in the system. No, you can diagonalize Tij, but I mean Tij, I mean I'm ultimately thinking about an infinite system, right? So it's an infinite matrix. So I'm trying to take the n going to infinity limit. Of course, for any finite n which you can do, you can diagonalize, and this problem you can easily do, right? So there is no problem of diagonalize. Hmm. Hmm. Right, so even in that diagonal basis, if you calculate this Green's function, so you can calculate all the Green's function, right, II and Ij. So you will find that this I, so if you do it for a finite n, you will find that those are down by 1 over square root of n, the I not equal to j. Okay, so n going to 0 limit, so those, sorry, n going to infinity limit, those don't contribute. Hmm. Yes, right. Yes, yes. Hmm. No. So without doing it, yeah. So like the Green's function. So I'm talking. So I'm only. So here I'm just trying to get the Green's function here, right? So of course, if I want to get other quantities and also, I mean, you diagonalize and all this, right? But what I'm trying to say that large n Green's function you can just calculate this way without need to diagonalizing and taking n going to infinity. Yeah, then you have to take diagonalize for finite n and then try to take n going to infinity limit, right? Yeah, you can go to the, yeah, exactly, that's what I'm saying. So you diagonalize, you find the new eigenvalues, you find this Green's function in the old basis, right? And what I'm saying is that this old basis Green's function you just can calculate, okay, by this method without diagonalizing. Right, so this Z0 doesn't depend on this thing. So this again, what Suvrat was saying. So essentially, you can see. That happened here also because essentially you can see that here also these Green's functions that appeared in this calculation, they don't depend on these Tijs, right? So I can independently average over these Tijs. So here also it's a somewhat different formulation, but same thing works. So you can independently average these quantities because this doesn't depend on the disorder, right, on these sides. And then when you average this gives you 0, okay, and then you only get the contribution. Now there is still one step left, and this is where sort of the large n comes, right? So the large n limit, the idea is, so this is of course a Green's function where this side is removed, but in the large n limit, because removing one side doesn't make any difference, all the sides will be similar, okay? So then this Green's function is same as the Green's function that you want, okay? So this is what the cavity method uses, this idea. That, so this is where the large n limit comes. So in this calculation, it's not clear where large n limit really comes. Right? So what I told you is just disorder averaging. So you might say that, I mean, what is large n there? But here the large n aspect comes because what you do is you essentially at the end you say that this cavity, what is called the cavity Green's function, where one side removed is same as any other side Green's function. Okay, in the large. So this is only true in the large n limit. Okay. Yes, right. Yeah, so that average is there, but even without this average, so let's say, yeah, that is true. So this average but I'm saying that this average you could have still done, right, without the large n limit. This would go to 0. But still to ascribe this to the Green's, so close the equation, right, because this is giving me an equation which is like G omega plus mu and T square G 0 omega, right. So to close this equation, I need to ascribe this G0 as same as G omega. Okay, so yes. No. So large n limit will work even without. So that's what I was trying to show. Even without disorder averaging, it will work. Okay. So see the here I although I wrote it average, but I should not have done it. I mean I don't really need to do any separate disorder averaging here. So this quantity itself is the average. Yeah, but these are independent realization. But yes, exactly. So essentially, this quantity is the T square, which is average over lattice size. Okay, and when you are doing this is also average over lattice size. This is going to 0. Sorry. No, so again, so right, so because these are random numbers, right? So this is where you can see that the correction is 1 over square root of n, right? So this will give you a square root of n here, and that gives 1 over square root of n, right? So if you are finite n, you are right. So there will be a correction, right? So that's the correction I was talking about. If you don't do disorder averaging, of course, if you do disorder averaging, by definition, this is 0, right? But if you want to get by lattice averaging this disorder averaging result, so then you have to take large n limit. Yes. Yeah, there could be always some rare realization which doesn't self averages, but they will be very rare. For a thermodynamic system, they will be of measure 0. Yeah, so typical realization. Of course, you can have a realization where all Tijs are same, right? So that's a very unusual, rare, but that can be there because I mean you can sample that, right? But that will have measure 0 for a thermodynamic system. Yeah. Typical realization. Yeah. Right. Right. Yes. Okay. Can I have the slides? Yeah. No, no. So here I really didn't need a Largen limit, right? I just use the disorder averaging without thinking whether it's valid or not. Okay.
So the statement is that you only get this nested Dij loop diagram, not in the larger limit, but because of the disorder.
Yeah, so here just disorder averaging seems to be enough if I am just using this set, right? Because by disorder averaging, all this will go to 0, right? Here, what I am trying to show that even without disorder averaging, if you are just doing lattice, that you have large number of sites you are averaging over this. So that will still happen, okay, without doing any disorder averaging. Okay, and there you really see the 1 over square root of n, the correction term to this. Yeah, so Largen expansion with disorder averaging. Yes, so really you are not requiring any Largen. I mean, this Largen you need for the SYK model, the interacting model. But here you actually seems like you are not requiring it. But actually, if you have to justify self-averaging, you have to take Largen. Okay. Okay, can I? Certain. Yes. Yes, yes. No, first term because you have T0 I square or mod square. Yeah, but this is just a positive number you are adding, right? So there is no, you are just adding n, so n positive number. So this quantity I am defining as T square. Yeah. Yeah, I have a 1 over n here, so it really goes, so is this just like average of this object? Yeah, so if I don't have this n, then it goes like n. Yeah. Okay. So anyway, so this is, so of course, because this is a simple problem, you can justify this Largen limit, right? In general, it's not true. It will be very hard to do it for SYK model. Okay, because you can't use this cavity method there. Okay, anyway, so you use the Largen results then, and then once you use the Largen result, then it's just an algebraic equation. If you write it in the frequency space, so you have g I omega and given by 1 over I omega in this object. So you can just write for g I omega in just a quadratic equation, right? And you can solve the quadratic equation. You can analytically continue this I omega into any complex number, and you can get a result, right? Just a solution of a quadratic equation. Now, of course, this result has this plus minus, so that you fix by looking into already you know some the properties of the Green's function, namely the way I have defined the imaginary part of g in this analytical continuation has to be less than 0, and also at large z it has to go like 1 over z. So by that you can fix the sign here, okay, which sign in which regime you have to take. So anyway, so basically you can calculate this, and now you can calculate. For example, the single particle density of state in this problem is the standard Wigner semicircle law. Just by solving this, and this is, I mean, this also gives you a self energy, because the self energy is just T square G by this definition, and that is just like IT. Okay, T is the hopping. So it's like self-consistent Born approximation that people do in many of these disorder systems. Okay, so now of course because it's a non-interacting model, so then everything is calculable. You can calculate in principle the many-body density of states, which is defined like that. So your many-body energies here is just given by these conserved numbers. Which is the occupation. So essentially you can create all the many body states which are the Slater determinant state by occupying this single particle state, and you can calculate this. Now, so there will be some ground state E0, okay, and then if you have to create an excited state, basically you have to change one of these numbers, right? So then essentially the change of the energy will be of this order, right, which is like essentially putting a single particle level spacing. So single particle level spacing is given by the density 1 over density of state into n, okay. So, so that means the excitation energies will be 1 over n here, near the ground state, okay. So essentially near the ground state you have, if you are looking into excited state, they are separated by 1 over n. Of course, in the thermodynamic limit this goes to 0, so this is a gapless system. At finite n, of course, it will have this 1 over n spacing. So you will see that it's very different in the SYK model. Okay. So you can do a few further things which I'll just go very quickly. So given this, so you can, so essentially by this method, this large n method, you can calculate the partition function, and then you can try to relate it to the many body density of state by Laplace transform, and then do an inverse Laplace transform to get the many body density of state. So this is the expression at low temperature for the free energy or the grand potential, and then you can do an inverse Fourier Laplace transform and obtain the density of state, and density of state has this characteristic form, okay, which is like square root of E minus E naught. So near the ground state it goes like square root of E minus E naught. But however, you have to be careful, because this result was obtained using some saddle point, which is not really valid at very low energies close to the ground state. Okay, so this result you don't expect to be valid at very small energies near the ground state. It has some regime of validity. Yes. Yeah, it's so if you look at the many body level statistics, it's Poisson. Yes. Yes. So if you look at the single particle sense, it's chaotic, because single particle level spacing will be Wigner-Dyson. Okay, but if you look at the many body chaos, then it will be Poisson. Yeah, here it is non-interacting. I have not put any interaction, so it's the ideal limit of a Fermi liquid. Okay, Fermi gas basically. This one, because this is how, okay, I didn't say that this is obtained using some Sommerfeld expansion. Okay, so that assumes that so it's just like a standard way you calculate specific heat of electron gas, right? So that's valid when T is much less than the Fermi energy. So that's basically the same thing. Okay, so you can actually see that at very low energies, this prediction doesn't agree, right? The prediction was a square root of something like that. At near the ground state, it was square root of this thing, but you have a tail here. Okay, so you can see that. Okay, so now let's come to the SYK model, and we'll try to contrast with these results. So this is the model which was originally, so originally this is a, there is a version of this model by the work by Sachdev and Ye in spin glass. So essentially they are studying some large SUM spin glass, Heisenberg spin glass, but these spins you can represent using fermions in that problem. And then that fermionic version will be very similar to what is written here. So Kitaev simplified it and wrote a Majorana version of this model, which is generally mostly used, but this version is also used because this has some additional handle that I will discuss. Okay, so essentially similar setup, that you have all the sites are connected to all other sites, but now basically using this kind of two particle hopping. Okay, so it's like an interacting 4 fermion term. So you destroy 2 fermions at 2 sites and then create another site. And again, for thermodynamic limit and all, you have to normalize this properly. And these are drawn from the disorder realization, Gaussian realization. So the main thing is, again, this model is solvable in the large n limit, and the main result is that in this limit it actually gives a non-Fermi liquid ground state, by which what I defined earlier, that this omega is much less than sigma omega at low frequencies. And then additionally, it has some very nice symmetries which at low energies appears, which is this very large reparameterization symmetry. And as a result of that, you also get, many body chaos, but sort of the maximal many body chaos, which satisfies this bound by Maldacena-Schenker and Stanford. Okay, so this all of this you can sort of calculate in this model, kind of simply. Okay, so that's a beauty of this model.
I have one question,
Yes.
Sumilan. So the Maldacena-Schenker Stanford worked with a unitary quantum field theory. There was no disorder there.
Yes.
So why would you expect the result?
Yeah, I don't
except
know
by
that.
calculation.
Right. Yeah, so again, I think the idea is that even this kind of object, this Lyapunov, the OTOC is self-averaging. So that's what you are assuming. Okay. So of course, to verify this, you can't verify it like this here, right? Because you have to. So there is no reason, as you are saying, there is no reason to believe that this is true. The only way you can sort of proceed, maybe you check it some independent calculation. So then you try to do this. So independent calculation here mean that you take finite n and do exact diagonalization and try to calculate this Lyapunov exponent. Now these people have tried to do. So with the method that people could use, like the exact diagonalization, people could go up to. For a long time, it was not possible to show even a hint of this. So generally, what people were finding that this Lyapunov exponent was just j. Okay, so it is not going to this 2 pi t. But people have improved this method, and now they are actually showing numerically this is coming 2 pi t. Now, again, I don't know the actual question that you asked, that why it should, in an average sense, it should still work, the bound should work. But I guess the idea is that each realization will satisfy this bound, right? Certainly, it cannot violate the bound. And then whether it is at the bound, that depend, you have to satisfy with other calculation, and it seems that those are agreeing. Okay, of course, Kitaev's interest, I think, was to write some solvable model for holography. But our interest in condensed matter is essentially, as I told, trying to use this as to distinguish different phases. Okay, this extra diagnostics. So this I already told. So you can, of course, write also a Majorana version of this. So I am going to work with this version, which is this complex fermion. And here again, there are some constraint because there is some anti-symmetry because these fermions have some anti-symmetries. So this coupling has to satisfy those anti-symmetric properties and also hermiticity. Okay. And if you do the calculation in this model and in this model at mu equal to 0, the large n result will be exactly same as the Majorana model. Okay, so so maybe I'll so I wanted to do some derivation here. Maybe I'll do it next measure. So just to sort of sketch out the large n derivation of these results. So this also can be obtained by this kind of diagrammatic method that I mentioned. But I'll try to work out, just briefly work out just how you obtain this large n saddle point equation using a field theory similar to this. So anyway, so I'll do that in the next class because today I have so let me try to go a little bit further with this, and I'll come back to this derivation. So basically you try to do a similar calculation here, but now you have an interacting term. So this become so you cannot really do a Gaussian integral and obtain the results. So what you try to do instead, that you write this action in such a way in terms of some suitable fields, which are basically what are called these bilocal fields. So essentially this action you can write in terms of completely, so you can integrate out the fermions and effectively write this action in terms of two bilocal fluctuating fields. Okay, so which has so now what you do here, you essentially take the saddle point because there is a large, so in the large n model there is a, you can write it as a large n sitting outside. So n going to infinity, the saddle point will give you the result. And so you essentially do a saddle point of this. Okay, and then you can get this equation, which, as I said, you can also obtain diagrammatically. It's a kind of Habermas. Yes, it's like Habermas. You can do it by different ways. So anyway, so this is the equation you get. Okay, so it's this is of course the standard Schwinger-Dyson equation.
Chen,
Yes.
is it same as the mean field approximation or different?
Yeah, it's what is in condensed matter language, it is what is called a dynamical mean field approximation. So it's dynamical because these mean fields are themselves functions of time. Okay, and its validity, yeah, it's a mean field results which is exact in this large limit.
Thank you.
Okay, so this is the only diagrams that remains in this calculation. And in this diagram, again, these lines are the Green's function, the same Green's, the on-site Green's function I wrote here, but for this interacting system now, not the same one here, but complicated object, but the self energy is exactly given like this. And here actually you can show that you need this, both the large N and disorder averaging to get to this diagram only. Okay. So this is your Schwinger-Dyson equation, this is the self energy. And in addition, in this model, I have this constraint that I have to also fix the number of fermions. So that is fixed by tuning the chemical potential. Okay. So what you can show by a very simple argument, given the structure of this self energy. Okay. So I'll show the self energy can be written in some way. So given the structure of self energy, what you can show that this model only non-trivial solution. So any non-trivial solution for this model must be gapless, okay, except these special points, which is n equal to 0 and 1, which essentially means no fermions and fully occupied state. So any other thing should be a gapless system. Okay, so this you can show by just from the structure of these equations. Okay, so it's a gapless state. So now. So let me just briefly mention, just to go in, before going into the analytical sort of review of this, just let me briefly mention how do you solve it, these equations numerically. Okay, maybe for some people it would be useful. So how do you solve? So it's a mean field. So as he said that it's a mean field equation. So as if you have dealt with mean field equation, you know that you just iterate and find the mean field order parameter. So exactly the same thing you have to do it here. So these are the equations. So now you can try to solve this in the Euclidean time. So again, these are some things you can write. So you can write the G tau and you can write the G I omega n and all this thing I already defined. So this is typically how you solve this cell consistency equation. Okay. So this is, as I said, that this is order parameter, but order parameter function, a dynamical field. So you start with some initial guess for the dynamical field. So let's say the non-interacting G tau, okay, which is just what I wrote here, the on-site G tau. And then to solve this numerically, you discretize it over tau, okay, so between this interval 0 to beta. So and then you just get this discretized sigma tau from this equation, okay, which is just an algebraic relation. So then you have to put it in these equations, but there is a complicated relation because you have to essentially do a, you have to take this sigma tau and you have to Fourier transform to get sigma I omega n. So numerically this is typically done using FFT, the first Fourier transform. Okay, I mean, so you do the FFT, so then you put it in this equation, you get the new Green's function. So there is an error here, it will be G inverse here, okay, so just correct for that, noting it down. So G inverse, so you put it in this equation, so you obtain the new G I omega n, then again you do a FFT to get G tau. So once you get G tau, again you get sigma tau and then you do this, okay. Yes, yes. So you have to solve the full function cell consistently, okay. You can find, if you, there are many places these details are given, you can find here. So you can also solve this in real frequency directly rather than trying to do in the imaginary or Euclidean time or imaginary frequency. So the idea is that this equation, you can write, you can just write in terms of the Masuvara Green's function. So just doing this Fourier transform, it gives a convolution. And then what you do to go to the real frequency, you use a spectral representation for this Matsubara-Green's function, which is determined by the spectral function, okay, which is given by the imaginary part of the retarded Green's function. So, so basically you use the spectral representation and then you analytically continue this I omega into omega, and then you can massage this equation and write it in this form. So what you will see that generally it will involve like integrations over 3 frequencies, okay. So to get self energy at a given frequency given a rho, okay, given a spectral function. So again the idea here is, yeah, I'll just end in 2-3 minutes. So the idea here is you start with initial guess of rho omega, again you discretize this, okay. So you have to do this some discretization over omega. So it's unlike here because Matsubara frequencies are already discretized. So you are having an additional discretization here, which is somewhat like this tau, but anyway, so you start with some initial guess, you discretize rho omega, and again you can use some FFT type algorithm to calculate this sigma omega, and given sigma omega, again you can calculate g omega and rho omega and iterate, okay. So this is how you solve this equation. Okay, so let me end with just saying, yes. No, so generally what happens is that if you go to this very low temperature, so it generally hard to converge, especially at 0 temperature, because in this problem particularly, because as you know that SYK model has this diverging spectral function. So the spectral function goes like 1 over square root of omega. So it's very hard to capture that at, but what happens at finite temperature, it gets cuts off by the temperature. So then you can convert. So generally what you try to do, you go from high temperature and slowly reduce the temperature. Yeah. You sort of do an annealing to get this. Okay, so let me just mention this. So this I would do in the blackboard next lecture. But so what so I'll just end with this, saying this. So what you can do, so you can, so as I said earlier that, so if you have a non-Fermi liquid, then the omega will be smaller than sigma omega. You expect the omega to be smaller than sigma omega when omega goes to 0. So now that omega term is exactly like this delta tau term, okay, in this base. So, let's say, so this is like an assumption. So let's assume that we will have a non-Fermi liquid, we can have a non-Fermi liquid state. So then this sigma will dominate, so you can initially just ignore this term, okay. So you rewrite the Schwinger-Dyson equation using, so you ignore this, you just, so this is G inverse, so then you just take the G other side, you get this Schwinger-Dyson equation, okay. So and remember that this Schwinger-Dyson equation comes with the self-energy equation, okay. So you have to solve it together with this, okay, satisfy it together. So what you can show that this equation, when you neglect this term, so it has very large symmetry where you can just reparameterize time using some monotonic function, differentiable function. You can just reparameterize the time like this, and then you can redefine, you can, so essentially you just do a variable transformation here. So replace tau by f sigma, so then these arguments will also be replaced. Okay, so that is this object, and what you can show that you can redefine your Green's function, a new Green's function, which is function of this new parameter or new variable sigma prime, which are in this form. Okay, so if you do that, then you will see that this equation remain invariant under this transformation. So in this particular problem, there is an additional invariance, which is some U1 gauge invariance, so that will appear. So of course, in the ultraviolet, this model didn't have this symmetry. So this symmetries only emerge at the low energies, okay. And in low energies, you have this very large symmetry. So in this complex fermion case, you have this reparameterization and this emergent U1 gauge symmetry. In the Majorana case, you only have the reparameterization symmetry. So basically that's the symmetry, and you can try to exploit it. So I'll try to discuss that later. So it leads to some low energy effective action if you exploit this symmetry. Okay, I'll stop here. Sorry.